So I'm very glad that quite a lot of people came to this tutorial. So we'll be giving a tutorial about a tool is called Poly, or I would say more about the general concepts we're using. So this tutorial will talk about how to do polyhedral optimizations. It will talk about a new way to perform polyhedral optimizations, maybe a little bit more structured than we did it before. And we're also going to talk about how we do optimistic optimizations to optimize code where it's actually statically very difficult to optimize the code. So my name is Tobias. I work at ETH in Zurich, and I'll be giving the tutorial together with Johannes Doerfert from the University of Saarbrücken. And we both work on Poly together, but at the very same time, it needs to be said there are a lot of different people working on Poly, so just because we are presenting here, that doesn't mean that's all our work. If you have any questions during or throughout the tutorial, so Michael has a microphone, just let him know, and feel free to interrupt at any time if you want to have something clarified, or if you want to have specific things explained. So I have a tutorial prepared, but clearly if you have specific things you are interested in, we can make this pretty interactive. So who has an idea of what polyhedral optimizations are, what integer set-based loop transformations are? So we have quite a lot of people. I'm still gonna do a little introduction in the general concept of what we are doing. So for such kind of people, it might be a little bit boring at the beginning. It might also be a little bit enlightening to see how we are formulating things. So yeah, just let's see. So yeah, quick overview. So the talk will be in 3 parts. We go first over the general concepts we are using. Then I introduce something I call schedule trees, or actually Sven Verdulage, one of our collaborators, introduced this kind of schedule tree concept, and we have it now in Poly, and I think it's very useful. And then the last thing, we just have a small picture, but Johannes has a lot of examples how we use in the end optimistic optimizations to increase the coverage in Poly. So let's start very, very simple. We just have a loop with a loop nest with 2 loops, and very simple loop bounds. But some of you may already see this as a triangular loop nest. Very simple. But still, I'm going slow because I think it's good to have the basics together, and then we're going to go more fast later on. So if you want to understand this piece of loop nest, the easiest way to understand this is just to mentally execute it, right? So to actually be able to execute this, you need to choose a value of n, because there's just like an arbitrary number of possible executions, and then we start executing it. So very simple, we start with I is 0, j is 0, and we have a first execution, statement execution that happens. And then we actually, even here, we want to increase j further. We realize we run into the loop bound of j, so we can't increase j further. We go to the outer loop, there we increase I. Then we can increase j, but only once. And then we run again into the bound of j small equal than I. So this is a super simple way to describe the loop execution, and if you continue with the execution, you'll realize you get 15 different statement instances that get executed throughout your loop kernel. So this is the first information we have, and this is actually the first point that I think is very interesting in polyhedral optimization. We really want to reason about each individual statement execution. So in this simple kernel, it's just 15 executions, but for an arbitrary program, it may be a lot. It may be a parametric number of such executions, so we need to find a way to reason about this in a dense manner. So if you look at those points, you may realize, sure, we can write this a little bit more concise. Specifically, this is actually a 2-dimensional vector space, where each dimension corresponds to one of the loop iterators. And then if you go again through your execution, you'll figure out that each of those statement instances actually is just a point in a 2-dimensional vector space. And looking at this vector space, we see we have a shape, and this shape happens to be convex, which is the case for a lot of loops. We also can handle non-convex things, but in this case, we have a convex shape. We look at the shape, we see it can be described by just 4 inequalities, and now you say, well, this is not super surprising. The very same inequalities actually are right in the loop bounds. So nothing new for you to be told. In general, this is not the case. A lot of constraints can be a lot more complicated. So loop bounds, which are just not small equal, but maybe have some modulo, or you have some Boolean conditions between those things. So in the end, the iteration space may become a lot more complex. But for this simple example, we really just have a two-dimensional vector space described by two inequalities, four inequalities. And now, I may even have been a little bit fast. So what we have now is just the set of compute statements, right? We just know what happens in this loop kernel. But we do not yet know, or at least in our model, we do not yet know when does something happen. And this is an important difference we make. So, and to actually know when something happens, we have something that's called a schedule. So this is also, in this case, super simple. We just map each individual statement, each individual point, again to another point, a two-dimensional, in this case, two-dimensional point in a vector space which describes the execution time. So here you see really we just have the original loop nest, and there's nothing surprising happening. But in general, you don't have the specific loop nest. So the variables, what was before I and j, may become something entirely different. So we call it C0 and C1. And then a very simple transformation you can do is to do a loop interchange. So you switch dimensions, and you see the loop or the code changes here by itself. And so I skipped the entire introduction of what poly is, how it works in LLVM. So for you, in a nutshell, what poly does is to make the connection between this higher level model and the actual LLVM IR. So what poly does, it reasons about LLVM IR. We are extracting this kind of high level information, this mathematical representation, and poly also, so you can play around with this, with the schedules, you can change the execution order, and poly takes care of materializing the changed execution order in LLVM IR for you. So if you want to do a loop transformation, if you want to have a high-level optimization that optimizes for data locality, what we propose is really to just reason on a higher level, to reason about the statements, the execution order, and then let poly generate optimal code for that. So let's go a little bit quicker. There's something we call strip mining. You duplicate dimensions, and now you execute in chunks of 4. You can do something similar, which is called loop tiling. So let's go a little bit slower again. So if you do loop tiling, what you do, you actually duplicate dimensions. The outer 2 dimensions, they enumerate different blocks of iterations, and the inner 2 dimensions enumerate the elements within the individual blocks. You already see the code gets a little bit more complicated. I never really worry about the complication of the code because it's done automatically. But for people who don't understand the code, that's how it looks. You just have a 2-dimensional triangular loop nest, and that's how you group it in blocks. So this is the complete polyhedral model. We have the iteration space, we have a schedule, and something I didn't talk about is memory accesses. So the only thing we have, or you get from LLVM IR, is the memory behavior of your program. So all the like 3-address SSA values, all the low-level IR computation, we don't reason about them and we abstract away from them. So the only thing that matters is the memory access behavior of your program. What's also interesting is if you work in poly or if you look into the poly program model, you'll see that almost all memory accesses are actually multidimensional in poly. So LLVM IR, you just have some kind of pointer expressions, but for a lot of optimizations, it's actually very useful to know that memory access is multidimensional. So assuming you want to do some code for example, you want to offload some of your computations to an accelerator. And there you maybe want to copy data. It's very useful to actually know that you just need to copy a rectangular subset of your data, then a large number of individual points somewhere spread out in memory. So multidimensionality is very important, and poly is recovering that. Johannes will be talking a little bit about that later. And then from this kind of basic information, we can derive more information. We can derive precise data dependencies, or we can, again, what I just said, we can, for example, derive which memory is accessed, or more precisely, you can actually, for each subset of the computation, you can derive the memory footprint. So if you look back at the tiles, you can say which memory is used by which tile, and this is very useful if you want to transfer, for example, just the memory of a specific tile. So there's a formal definition of the kind of spaces we use and play with. I just wrote this down for you. What we have quasi-affine expressions, Pressburger formula, which are formed from quasi-affine expressions, and then we have something called a Pressburger set and a Pressburger relation. I don't actually read what we have there because it's kind of a lot. But let me see if I can get into something more interactive. Let's make, so this is super interactive. Just need to copy the right things. And then we can get this started. Jump. Right. So as I said, I won't really talk too much about poly itself because I think it's more interesting to look at the higher level concepts. But Johannes will show a couple of poly examples. So I just said we have sets and maps and Pressburger sets and stuff. So let's just try to explore what they are. So let's just try to reproduce the example we had before. So we define a set going from, so this one has one parameter. It has a statement, I and j. And we have, so that's the iteration space. And what else did we know? We know that 0 is smaller than j, and j was smaller than I, right? So this is the set we have. We can just generate it, and if we want to have a look, we can plot. Okay, this is an interactive tutorial. All right. Interesting. So does anybody see why I made a mistake? What is the mistake I made? I like this interactive because I always make mistakes and then people can fix them. Why can't I plot this set? How many points does this set have? More than 100 or less than 100? Less than 100? I think it has a lot of points. It's actually not even known how many points it has. So let's actually assign our variable n a value. Let's make this 8. And then we can do something like, right? Okay. Oh la la, this is big. Let's make this a little smaller. All right, so now we have the three-dimensional iteration space, and we know how it looks like. And now we can really, this is a lot of the stuff you really, I think one of the things you should take away from this presentation is really a lot of the reasoning we are doing is graphically, or at least can be done graphically, and I think that makes it a lot easier to reason about such things. So what can we do? What else can we do? So I said there are integer sets of points, but there's also something we call an integer map, which, for example, takes a point ij and maps this point to another point I j plus 10, right? So we just translate this set of points somewhere in the space. So this is a map. This, again, does not work because I have a typo here. And so what we now can do is we can define a second set that just is derived from the first set by applying this map. And then we print the second set. And nice. What you see is now we have more points. And this is all we reason about are just sets. So it's clearly something you can do with all those sets is, for example, you build the union of two sets, S and S2. And we don't even want to print that, but what we can do is, for example, create the convex hull of all of this. And this is our hull. And then we have something like plot set shape. And if we are lucky, we get the entire set of points. So this is something, again, it's super simple if you just reason about sets. But if you want to generate code, if you want to do something with your compiler, what happens very often, you have a some points, some data elements you want to copy to your accelerator to a different address space, and then you figure out this set is not dense. It actually has, like this, it has holes, it has something. So the question is, how can I copy, which data do I want to transfer? And a reasonable thing, you normally want to build some kind of rectangular hull, because this is a lot more efficient to copy data. So now we have some things. Let's play a little bit more. And then we need to go to schedule trees later on. Let me copy the right thing. Yeah, okay, this is not fully right, but so we can pretty print a lot of the stuff. And here I forgot an implementation. This is just a couple of pretty printers that help us to see what we are doing. Let's call this map. Nice. Okay. And so now we just saw we did the transformations. We previously saw on the slides some kind of transformations. I just showed you the set of points we had, and now it would be interesting to actually generate code for them, no? To generate code that executes whatever we just built. And so the first thing we need, as I said before, we need a schedule. If we are lucky, we still remember that our points were in something called ij, and this we start off with. It's always the identity because it's simple. And then we do something. So no, let me print cmap. All right. So this again gives us an error. This is good. Was not the error expected, but so this gives us an error. Do you understand why this gives us an error? This is learning by error. So I don't let you wait too long why this gives an error, but clearly we again try to generate code for an infinite set of points, so that doesn't make any sense. But what we can do is we can actually constrain our, so you see it's just set operations to intersect the domain. So the first part of our relation is called the domain, the second part is called the range of this thing. So if we intersect the domain with actually the set of program statement instances we want to execute, S1 is not defined, so how did we call it? Just S. Right. Then you see we can generate code for that. That's very nice, no? And then let's just quickly do the kind of things I did before. Let's do the interchange. Did anybody see the interchange? It's not very clear, but this loop now starts at C0, and if we have it the other way around, so this starts at C0 and goes up to 8, and if you do the other way around, it starts at 0 and goes up to C0. So this is the kind of loop interchange you could do. We could do something like loop tiling. So don't make it too complicated. Jmod 2. And we get some loop tiling. So those are simple program transformations we can do. So like, can we illustrate them? Sure, we can. No. All right. So this one does not work because lines 2. All right, and here's the kind of tiling we had.
So why don't you get parameterized code?
Again?
Why don't you get parameterized code?
Why?
Why is it not print if you don't say n is 8?
The reason is because for pretty printing, I had to fix the value of n. But
shouldn't n just be a input?
Right. So this was to make the pretty printing work. So if you just keep this unparameterized, let's just copy this straight below. You get precisely what you want. So this is the code parameterized in N. So yeah, this goes maybe a little bit too detailed, but in general, what you can do, in general, all the parameters are kept free. So like by default, everything would be generated as general parametric code. But you can sometimes provide information about parameters. For example, if you know all the parameters are even, a parameter is known to be positive, this often allows the compiler to generate better code. Specifically, you can use bitwise computations if you want to implement a modular stuff. So you can provide this information in this context, and it will be exploited. All right, I think that's enough from the basic things. Otherwise, I don't get to the schedule trees. So let's go very quickly. So we understood what those kind of things mean. And then there's a general question I just briefly want to address. People say all this kind of what we're doing is super slow. Well, this doesn't follow my slide order, but it's often a concern that a lot of the integer computations are slow. So just talk about the complexity first. So first of all, it's interesting that a lot of the stuff we are doing is actually super complexity-wise super expensive. So it's double exponential in the number of loop dimensions. So a lot of the computations could be theoretically very slow. But interestingly, first of all, for compiler stuff, it's not so problematic because the dimensionality for us mostly grows with the depths of the loops. And in most programs, the depth loops are actually not so deeply nested. Second, for a lot of the inputs and operations we're performing, we actually don't get in this worst case where we get double exponential stuff, but most of the things we solve are pretty fast. And in general, we can bound in general, for the rare cases where we actually run into performance issues, we can stop this or like detect this and just bail out. So it's mostly a missed optimization stuff, but it doesn't happen so often. But yeah, why Pressburger stuff? Why did we just choose such kind of representation? And the main thing here is, I think that's just the best you can get. It's theoretically the best you can get. It's as generic as you can get while still being computable. So if you go to some kind of polynomial expressions, a lot of the precise information we are computing, it's just not computable anymore. And within the bounds of Pressburger sets, you're closed under most operations, and it's a very nicely well understood mathematical domain. So regarding complexity, I think this is under control. And the question is, can you actually, if you're very clever, can you do better by just writing specialized compiler passes? And I think in general, it's impossible because if you want to have generic dependence analysis, it's just an ILP problem, so you need an ILP solver to solve it. Clearly, there are a lot of cases in a compiler where you don't need the full generality, and there you can go very well with heuristics. And that's actually what we do in those libraries as well. So we match for common cases, and those are pretty fast. And then if you go in the general case, sure, you're solving a difficult problem. But this is kind of the theory we're working on. Something it's difficult to understand. Sometimes it's also the model I just presented you indeed is sometimes a little slow. It's also difficult to reason about this in the terms of like classical loop optimizations, how you do loop interchange and like if you want to do register tiling, how do you do this if you just reason about schedules? So I just explained to you some of this, but in general, I think it's still maybe not the most straightforward way to reason about program transformations. And this is something what we've been working on, what I think is a pretty neat compromise, or I think it's maybe even better than a compromise, and we call this a schedule tree. And the idea of the schedule tree is that you actually, instead of having this just schedule relations which you need to reason about and try to understand, we have this structured schedule that starts with a set of iterations you're executing, and then has different nodes that you define different parts of your schedule. So some of the nodes are really just the mappings we just have seen, but other nodes directly give you and tell you that there is a sequential order between certain statements, certain parts of your compute kernel. And this is actually, it's very neat to play around and to try to understand what's happening. for a human being, but it's actually also very, very good for writing fast compiling code, or writing a fast compiler. Because before, with the original input I just showed you, all the questions we reason about boil down to an ILP problem. You ask which iteration is before the other one, and then you compute a lexicographic minimum to find this out. So this in general, even though we can be fast, it's still a lot slower than just looking at a tree and see, okay, there's a sequence and this one is before the other. So you can really pattern match on the tree, and you can have a lot of the information you want to derive just directly get from the tree. At the same time, you have the full expressiveness of Pressburger sets. So I think it's more convenient to work on such kind of tree than to work on LLVM IR, where you do one transformation, you change the IR, and step by step the IR becomes more and more complicated. So for us, we have the full constraints, and we have, like, we keep track of them, we simplify them, we modify them, but we always have something we can reason about until at the very end where we materialize the code. And so for the very last thing of the talk, I just wanted to briefly show you something we recently implemented in Poly. It's outer loop vectorization. We re-implemented it using schedule trees, and I just want to go through with you how we did this and why I think maybe it shows that it's a useful way to reason about such kind of transformations. So we just start with this simple single statement loop nest again, and just imagine the I and J loop are parallel, and the K loop is sequential, and we want to do some kind of tiling, and afterwards we want to do some outer loop vectorization. So how do we go about that? Well, first of all, we do some kind of tiling. So tiling is very simple in this case, but in general, if you have a big loop nest, how do I tile a big loop nest on a scheduling map? It's difficult. I mean, here it's really simple. You just identify the node which you want to tile, and there's just one node, so it's very simple, but it doesn't fit on the slide, but the bigger the tree gets, the more complicated it is. So we have just a tiling, and now we have two nodes. And as you see on the left side, the code changes as always, and then you can play on those nodes and just say, okay, we probably want to do something more with the inner nodes, because that's where we want to do the vectorization, so we want to do something more. So let's just get more individual nodes that we can reason about the individual nodes and perform per node transformations. And so how do I implement outer loop vectorization in general and specifically on such kind of tree? This time nothing fails, but you still need to answer it or figure it out. So what is outer loop vectorization? How can you describe it with the kind of transformations I just introduced before? Again? Right. It's two pieces. So the first thing is you want to strip mine the loop. So you want to partition the loop into the parts of the computations that are executed in different vector elements. And then each vector element is performing 4, 8, 16 operations. So you want to partition those things. And then you want to have the part that describes the computation of an individual vector instruction. You want to move this one, you interchange this one to the innermost level. And that's precisely what we do. So we have this additional level of strip mining, and then you see this band kind of drop down to the innermost level. And on the left side, you see we have a nicely, perfectly vectorizable code. So this iteration is fully parallel. It has as most 8 iterations. So we can map this nicely to a vector instruction, right? Actually, it's not so easy, because now we have something that sometimes wants to execute 8 instructions, sometimes you want to load just maybe 5, maybe 3. So this doesn't really nicely map to vector instructions. So what's the next thing we want to do to actually make this vectorizable? So if you just think of writing your own vectorizer with default LLVM IR transformations, what is necessary for this? Right, you want to peel that. And this one is actually, for vectorization, innermost loop vectorization, you can just write this yourself. And most likely you can write this yourself for a lot of things. But what we do is we have some kind of generic facility which just says, please separate whatever is a full tile or a full vector operation from whatever else, from what is not. And like this, you get like the simple vector loop, which really always has 8 iterations. And here the code didn't fit on the slide. It's not so big, but it just didn't fit. But this is the peeling loop. And this is very nice because now I would need to go very back to the first. But if you remember this slide where we did the tiling, there were a couple of tiles that were full, and then there were all the small partial things. And in general, you can use this isolate option to always generate good code for the core computation, and then you get all the cleanup code on the side. So this is optimizing with schedule trees, so it's a lot faster, like compile time-wise. You can implement a lot of classic loop transformations. If you have an idea how you want to optimize your program, you can use schedule trees, you do interchange, strip mining, fusion, fission, all those things, and it just works. What I think is really cool is that you can actually, similar to maybe not similar to the selection deck, but somehow you can do peephole optimizations. You go over the tree, you identify certain nodes where you know what you can do, and you just do it. You can only decide to only optimize a part of the tree, and if you do want to do something really complex, so there are a couple of advanced things I didn't present to you, but if you want to do something like offload something to an accelerator, there are a lot of very useful operations to do that. So we'll be changing right now, so I think the camera guy needs to change the laptops. So Johannes will be talking now about optimistic optimizations and actually look at a lot of more source code, a little bit more of Poly itself, and see what the kind of the basics, the elementary elements I presented. I think he'll show how we use them now.
Is that good? Okay. Yeah, it's like showing time. Okay, so let's look what we have. The problem we have in Poly is that we do everything statically, and statically a lot of things you can't really show. And because we try to extract exact information about control flow, memory accesses, and reason about them, and do transformations, especially transformation part is hard. As soon as you start over approximating, you're pretty much done. So as soon as you start over approximating your accesses, your control, anything, you can't do that much anymore because you have to assume all the bad things might happen. And there's a lot of bad things that might happen in a program if you only look at the semantics of the IR. But programmers are usually really nice and they do not exploit all the really bad facts about the IR. So let's look at some of them. So let's just look at what we do. So first thing is we take optimistic assumptions during compile time, so during static time. So we have identified a couple of cases where we would like things to be nice, better. And we will just like assume them to be nice and better. And then we derive conditions so that they actually hold. So about these conditions, at runtime, we have to check if these conditions actually hold. So we don't know that yet. So at compile time, we figure that out. It would be nice if X holds. At runtime, we will check X. So what we do here is we version the code. Oh, wait. Whoa. We version the code so that it, no, this is not right. Wait, sorry about that. But that doesn't work that way. Why isn't this working? Is it? Just like, okay, sorry about that. It's like still a little bit. Anyway, so what we do is we speculatively version the code. So we have like a runtime condition we generate statically, and if that holds, all of our static assumptions will hold. So statically we can't show it, but we will assume it. We will build a runtime condition statically, and we will like version the code in currently 2 versions, like the good version and the original version. So, and what I will show you how, what conditions we actually take at the moment. And but these conditions have to be fast at compile time because we can't spend too much time there. They have to be fast at runtime because if they fail all the time, we will add overhead. Even if they don't fail, we might add overhead. So that's like bad. But what we figured out over the time, so we did experience and so on, most of them are with a high probability true. So it's like we take assumptions you will see that are like programmers do too. So we basically look on the code like a programmer would do, and we just ignore the nasty facts that might occur, the nasty things that might occur, but some people even don't know about that they are problems. So let's look at that. So we have two categories of assumptions here. Those we need to actually represent the code in a sound manner, and those we need to get some better optimizations out of the whole thing. No aliasing is pretty clear. So as soon as two arrays alias, we don't even know what is like who's accessing what. So if they overlap in some sense and so on. So we will rely on LLVM alias information, but at some point that gives up. And after that, we have to either assume every memory location that is accessed through A is the same as a memory location accessed through B, or we assume there's no aliasing going on. And let's be honest, who wrote code with aliasing intentionally in his life? Like, it's usually the case that that doesn't happen, but we still have to check it. So the next one is the no wrapping assumption. So IR doesn't prevent us from wrapping in signed or unsigned cases. Like C says, okay, signed isn't allowed to wrap. That's like undefined behavior, so on, so good. But LLVM IR, it can wrap in signed and in unsigned cases. So that's like kind of a problem, because if it wraps around, you get back to an old value. And in our model, everything goes just like our model isn't fixed bit width. So we have like a continuous math model. We could add the modulo constraints into our model, but that would make the compile time really bad. So we don't do that, but we just assume it doesn't wrap around, and it often doesn't wrap around. Then we have the finite loops assumptions. Sometimes you have loops where the trip count isn't computable. So you don't know if the trip count is like a finite number or not if you assume no wrapping. So like it will stop eventually because of wrapping, but without wrapping, it might have like an infinite number of loop iterations. Array inbounds assumptions and valid multidimensional view assumptions is, the question is, if you access an array, in the sense you should access an array. So like, do you treat it as like just a memory, and the fact that it's an array is completely ignored? So array of 128 times 128, you can access it with 129.0 as an index function. That's fine in C. That's completely fine. Something like that. So you can do stuff like that, but you're not supposed to do. And we will assume people don't do that, but we can't always prove it. So we have to add some assumptions. We have the array inbound check hoisting, parametric dependency distance, and possibly invariant load hoisting as last three optimizations. So I probably don't have time for all of them. So let's go through 1, 2, or 3 maybe. Let's do the alias thing. Aliasing is kind of funny. So alias thing is not as all the others, because aliasing is talking about the memory space. But what we do is, for example, here we have a loop. I will always present like a little example, and I mark what I want to do. I want to vectorize this loop, and it looks vectorizable. Yeah, sure, as long as there's no aliasing. So as soon as there might be aliasing, we can't vectorize that loop. So what we do is the same that the LLVM loop vectorizer does. We will assume that the arrays do not overlap in the range they are accessed. We don't really care if they are accessed in the same alloc malloc call and so on. As long as during our loop they are not overlapping, like during the accesses, everything is fine. But we can't, so while the LLVM loop vectorizer does that for innermost loops to vectorize them, we do that for the whole loop nest. So we generate, like in front of the whole loop nest, we generate once this check, and afterwards we will mark everything in the optimized version as no alias, as alias free. And that will also enable other LLVM optimizations to hoist loads, to vectorize stuff, and so on. So they will profit from our annotations. And we can do that for anything that has affine functions. As long as everything is like affine, we can always build those alias checks. So, and we don't only look at the simple, okay, what is accessed, but we also incorporate like domain knowledge, for example. So we have the odd and the even iterations here, and they are never executed together. So we should, like the odd and even, there are two things. So first, odd and even are never executed together, or accessed together, and these arrays are only read. So we don't have to check the read-only arrays like against each other, and we don't have to check odd against even because they are never accessed in the same execution of that thing. And that's what's going to happen. So we will try to, because if you check each array against the other array with the minimal and maximal access, you will grow exponentially. Then you try to split it up into groups that you kind of, with the number of groups, you grow linearly, but with the size of a group, you grow exponentially. So we try to split it up as much as possible, which is basically boils down to those two cases at the moment. We could do it more, but these seem reasonable for general code. Okay, let's go. What do we have here? No wrapping assumptions, so let's a little bit faster. So this code looks perfectly fine and could be vectorized, but as soon as n is bigger than 128, like for chars here, this expression will wrap around and will actually create a loop carried dependency. So like that's in general, we will do that all the time. What we will do is we will look at all expressions and we will figure out if LLVM already knows that it's not wrapping, like the NSV, NSW flag, everything is fine. But if it does not, we will compute the expression twice, once in original. Oh, wait, I will actually have slides for that. So what we ask ourselves is the expression the same mod 2 to the power of k, where k is the bit width of the whole thing. So does it still fit into the whole thing? Like, yeah. So in this example, okay, I is between 0 and n minus 1, n is between 0 and 2 to the 8. When is this expression true is what we ask and what we compute, and which boils down to n is smaller than 128. So we will add that expression to our runtime context, and we will check it at runtime. But we can now assume there's no wrapping in the whole thing. So yeah, that's kind of neat. What do we have here? So yeah. So what's the problem here? Still, again, like one loop nest, vectorize the whole thing. Everything should be fine. Problem is that we compare with I is not equal to n, which people usually don't do when they write code. They write I is smaller or equal to n, but a compiler, LLVM, will actually introduce a not equal condition a lot of the time. And so only if n mod 2 is 0, then this will be optimized, because otherwise we get the wrapping and infinite loop otherwise without wrapping and so on. And we don't want that because it has a lot of problems. So yeah, infinite loops are figured out here. Okay, what do we have here? Oh yeah, here's the array in bounds check. So we see that there's an array with fixed size, like in C given. But when we access the whole thing, these are parametric accesses. So we don't know statically where we will access. And so what we have to, because we want to treat that array as a multidimensional array, what we have to guarantee is that the user treats it as a multidimensional array too. So he doesn't do out-of-bound accesses to access different rows in the array. And that boils down to checking that n is smaller than 128, because this equality holds true. So you can access the same location with different access functions, and we don't want to do that. That gives you the same problems as aliasing. So from there on, we don't know what accessed what anywhere. So we will add these assumptions here. Now this is kind of the same problem in harder. So often C programmers linearize their arrays. So they don't have, or if you have before C99, you have a parametric sized multidimensional array, you linearize it yourself, and then you compute this, access function yourself from a linear into a multidimensional way. So now you have the same problem as before, obviously, because we want the multidimensional view of that thing, so it shouldn't access the different row through multiple accesses and so on, and multiple instances. But we first have to come up with the actual multidimensional sizes. So how big is each dimension? So that's actually will happen. So it will kind of guess dimension sizes, and then it will ensure that they are not accessed out of bounds. So yeah, same here. So this is like the most generic case where we access a multidimensional array subset-wise only. Okay, what do we have here? Oh yeah, this is pretty recent. So let's assume a safe language like Java, Julia, or whatever. And what you have there is, if you don't turn them off, you have array out of bounds checks for each array access. So it has some kind of safe array, and what it does, every time you access it, it will check if the index is smaller than 0 or bigger than the size, and then it will throw an exception, which in LLVM will call a function and then have unreachable for Julia, execute unreachable for Julia, and so on. So something will happen that is bad. So, and if you now have your loop nest with these with these exceptions in there, you're probably not going to do any transformation. So, but what we will do is we will figure out, because these bounds are fine, we will figure out that throw out of bounds is bad. So basically everything that is a function call is bad in our world. So we will say, okay, that's bad. Let's assume it doesn't happen. And what will happen if we assume it doesn't happen is that we will have an optimized version which doesn't check the array anymore. It will just plain access the whole thing. And it will only do so under some conditions. So because here, you again have a kind of trigonal loop, then the condition becomes kind of complicated for people to write down. But the whole point is you can hoist all these array out of bounds checks for Julia out of the whole loop. And you can, other function calls work too. I was going to show an example. Maybe I get to that. So we can hoist everything that is a function call or function call-like out of, if it's guarded by affine expressions. And that will happen basically automatically. So this is like another example. So sometimes we've seen benchmarks where people put something like this in there. So the benchmark contains some error handling or some special handling for debug cases. And now this loop is basically sequentialized. The outer loop is sequentialized because you might call a function here with side effects. So you're done. But what you could do is you can parallelize it if you assume debug level is smaller or equal to 5, and that's what's going to happen. So Poly will assume side effects from function calls do not appear and hoist the condition out in front of the loop nest and execute the optimized version then if it actually is the case. Otherwise, it will execute the original version. So now what do you have here? The vectorization, okay, So if we want to vectorize with, say,
Johannes?
Yeah.
So for the out-of-bound hosting outside, so if someone wanted to just add some light, if someone wanted, there's a bug or something, then they will not see it because as soon as they turn the printf, they will run a different code. Right? They would run
this will run different code in debug and in release mode, basically. So totally right. There are different ways to deal with that if you don't want that, but by default at the moment that will happen.
So you may need the alias check on the array store and the debug level, right?
Again?
So you may need the alias check on debug level and the A array so that they don't overlap either?
Yeah, you can do different things. You could, for example, make a dummy call here or something. Anything that makes this the expression not the guard non-affine, then we are not going to do anything because we can't. Something like that. But then we don't optimize the whole thing anyway. So now, as long as it is in there, we are not going to optimize it. So now you have to choose between optimizing it and allowing us to remove it, or not optimizing it at all.
No, what I'm saying is that debug level was checked in every iteration, and now it's checked once. So if A, if
the hoisting will remove the checks. So it's same for the example before. So instead of checking each array access to the safe array, we will check the array. We will check only once if everything will be in bounds, and if everything is in bounds, we can not check at all.
Your point was the debug level variable may alias with A and B. So we actually, So I think we actually do this. I'm pretty sure we're doing this, but this is not in the example. So this example doesn't have runtime alias checks because it's just to illustrate the hoisting, but clearly to make this correct, you need to have a runtime alias check between A and B, and at the very same time, you also need to check that there is no aliasing between debug level and the other step.
So if there might be aliasing between anything, it doesn't really matter if we hoist it, if we access it inside, if we don't. So everything is guarded by alias checks. If LLVM can't alias information doesn't guarantee us it's not aliasing. So if debug level might alias with something else, we will actually preload debug level, then check the alias checks, and at the same time, the debug level is smaller. So all the checks, and then only if everything holds, then we know it is actually alias free, and debug level is small enough, and then it's invariant. Then it was okay to preload it. So yeah, here it's like it is a load. Yeah, it will be preloaded and then checked. Yeah, you're right. So here we have the parametric dependence distance. We can vectorize that if C is bigger than some value. And lastly, that's actually now that goes into your direction. Lastly, if we have like loop bounds that are loaded, so that's like we have invariant loads. We can hoist invariant loads, but the really interesting case is when the invariant loads play into our scope description, so into description of our model. So if we don't know how many iterations these loops might have, it's kind of hard to build runtime alias checks. Basically impossible. So and without runtime alias checks, loop invariant code motion might not be able to hoist that load. Okay, so we need to know the value to build runtime alias checks to argue that it was okay to hoist the whole thing. So it's like a chicken and egg problem. So you have to kind of do the aliasing runtime alias checks, if you need runtime alias checks, and the hoisting at the same time. So in this example, which means that we will hoist size 0, the load of size 0, and preload it. Then we will also hoist size 1 and preload it because we have to assume everything is invariant anyway. We can't deal with varying loop bounds, so we have to assume it's invariant. And we have to make sure that we only access memory we would have accessed anyway. So that it's all sound, all good. And but the point is now we can use these preloaded values to do basically runtime alias checks if they turn out to be okay and all the other checks we need that everything is fine. Then we know the preloading was okay, and we can and the assumption that it is invariant holds, and we can use those preloaded invariant values. Otherwise, we go back to the original code and do everything as it was before.
In this code, you assume that you have no threads that modifies size 1 and size 0 in between.
Again? Oh yeah, this totally breaks if you have threading.
Okay.
So like a lot of things, we do not. So what we don't do is we don't consider like atomic operations or somehow like memory operations with a concurrency model. So if a memory operation has a concurrency model attached to it and some kind of then we just bail out. So we don't handle it. So what we assume is if it does not, there's a data race free program and we are good. And that's the base assumption. As if there's a data race,
If there is a race, we don't handle it in LLVM anyway here, right? For single lines. I mean, the compiler can preload or anything, so it's a safe assumption.
I could show you like.
For thread, it needs to be volatile. I mean, if you'd actually have to make that volatile, I think. Yeah, but it's not volatile. So.
Let me just show you something. So this is like from the NAS parallel benchmark suite, and so this is the whole. Can you see that? Yeah, this is the whole kernel of one of the compute functions. So it goes like this for a couple of hundred lines. I don't know. There are bigger ones that look basically the same, but yeah, you get the idea. And in between those, there are, for example, like here, there are these timer on calls. So somebody put like these debug calls in there that sometimes like take timer values and so on. There are these multidimensional arrays or things that are used as multidimensional arrays at least. So we need to figure out, and all these the loop bounds, as you see, they are all loaded. So we have to preload loop bounds to figure out the alias checks and so on, and to actually like, assume them invariant and so forth. Then we have to look at the values we preloaded to figure out that the multidimensional accesses stay in bounds. Then we have to assume that timer on is not set, so we can look at the whole program, the whole kernel as one thing, instead of looking at different smaller kernels. And we have some like overflowing issues here and there, which are like in this program, like in most of the programs, not real. So we get overflowing if some values are close to the boundary. So like, oh yeah, and the value you load has to be smaller than 2 to the power of 31 minus 5, something like that. So we get overflow conditions like this. Currently, we still generate them, so they are like not really useful, but anyway. So we know that our input doesn't have overflows. But for programs like this, I just wanted to show you that most of these things have to play together, and we need all of them to statically analyze in a sound way all of these nice codes. And yeah, I guess we're out of time, huh?
Just one more thing to add to this framework. So basically, for example, for the aliasing, once Poly figure out that aliasing, once it's create the version without aliasing, we put the annotation for the alias scope so that the SQL LLVM optimization will work, and then we'll optimize and do the hosting and all of that stuff. So if there is other annotations, they could be put in the IR so that they are simplified.
Yeah. So just maybe it's interesting for some of you. So here the list of invariant loads begins, and basically all 3 lines means that we will hoist another load from this whole function. So we will preload a lot of values, including these loop bounds that are used everywhere. And so they're quite like 30 or 40 values that we can preload in the beginning, and then we have some. Now here are the contexts we build. So we have three of them: context, assumed context, boundary context. Context is what we actually know about the program. Assumed context is what we assume about the program, and boundary context is what we assume about the program, but it's probably not useful for anything except being sound. So the boundary context contains things like it's no overflow. Usually like conditions that are just make everything harder. We have to check them to be sure, but they're not useful to optimize in between. Assumed context, we can use them to simplify stuff in between because we already assumed something is true. And then we can use that to, for example, simplify dependencies and so on. And these just make it harder. These don't. And context is what we already know, as I said. And yeah. There's one part of the assumed context that is actually useful. Everything else is just boundary cases. So if, for example, nothing is executed or some of the loop bounds are always 0, that are cases in there, but one case is actually interesting. Yeah. Other questions? Yeah, there's one.
Can you go to your slides?
Yeah, sure. Which one?
Last one.
This one? Or this one?
Yeah, this one. Yeah, this one.
Yeah.
What if size 0 and size 1 is overlapping?
Oh yeah, we have runtime checks as soon as we have may aliasing between any 2 pointers, we insert runtime checks. So we will figure that out. So we will still preload them. Then we will figure out that they might overlap, and then we basically bail anyway. Well, size 1 and size 0 we wouldn't even bail because they're both read-only. So otherwise we wouldn't have preloaded them anyway, because if they're not read-only, they're not invariant. If they're not invariant, we can't preload them. So if we preload something, it's read-only, then we don't need alias checks. But if there's some size might alias with an array, we will have alias checks in between. Preload, then alias checks, then optimized version or original.
But in order to generate alias check, right, this size 0 val and size 1 val should be exist, right?
Yeah, we might access stuff to, yeah, we have to access the sizes to generate the runtime alias checks. That's the point, because we can't just like do one, then do the other. That doesn't work. We have to do it at the same time, basically, yeah. We have to assume they're invariant, preload them, do the runtime alias checks, and then check if it's true or not.
Okay, and in the false path of the alias check where pointers are overlapping, so in that case, your trip count is size 0 val and size 1 val. Instead of these, you will have size 0 and size 1.
Yeah, we will execute the original code. So that's not shown here. So we will execute the original code as shown in the slides before. So if a runtime alias check fails or any other check fails, execute the original code we didn't touch. So, yeah.
Thanks.
Okay.